my thanks. So you may answer him directly. So because we have next talk on the, and that is by Rakesh Kumar Singh. Thank you.
Professor Watanabe, I will answer your question by email. Please drop me an email. I will answer you. Thank you. Sorry about this.
It's a straight meeting. So please, Rakesh.
Can I share my slide?
Yes, of course.
Okay. Hello, can you see the slides?
Not yet.
Okay, wait.
Yeah, we have your slides now.
Is it okay?
Yes, perfect. Thank you.
Okay. So let me say thank to the organizer, particularly Professor Yoko Miyamoto and Dr. Kali, for giving me opportunity to virtually share my work and interact with researchers and students from UEC. So this is the title of my talk, where we will discuss scattering assisted imaging. And I come from the institute in the northern part of India. We call the city is Varanasi, and I work in the Indian Institute of Technology, BHU. Okay, so okay, so this is the major objective of the work. Why we want to do this kind of work? What are the opportunities and challenges? So our major objectives presently are to build imaging system with random light, and deal with a situation where you have the randomness by choice or randomness with compulsion. So we'll discuss few of those topics in my presentation. So before going to the presentation, let me why it's not moving. Okay, let me just briefly touch my close association with UEC. I was a postdoctoral researcher at the UEC during 2009 to October 2011, and I thank Professor Takeda and Professor Miyamoto. I learned a lot, and some of the work which we did at the UEC. And this is the picture of Professor Takeda visiting us long back, I think 2018, and Professor Miyamoto in 2019, probably in 2019. Okay, so this is the outline of my work, where we'll discuss some of the challenges, particularly imaging through the scattering media, and then we'll discuss how to overcome the scattering related issues by learning from the physics based approach, particularly using the coherence optics, and then we'll discuss some of our works. Okay, so if I go to the basic of the imaging, I think the audience may be aware of the diffraction limited condition. If you have the limited size optics, the diffraction limited, we will get the diffraction limited image in case of the good quality wavefront or good quality optics. However, the major issues come when we have the scattering in the path of the light. So in the context of the imaging, we have many imaging systems. Some of the imaging systems I have discussed here. And this talk I will try to cover mainly the holography. So I will discuss few of the holographic principles. First in the conventional holography, and then we'll discuss how we can take the holography with randomness. So when we say the imaging, the content of the frequency spectrum, which we are dealing with, that decides the quality of the image. So the question comes that how cleverly or how nicely we can use and extract the frequency spectrum, and that will decide the quality of the image. So if I have the object, so this is a very, very fundamental explanation. So if I have the object, it will have the components of frequency components, and depending on the nature of the optical system, some of the frequency components will be involved in providing the information which we require. However, there will be some loss, like evanescent frequency and those things I'm ignoring. But apart from the evanescent, later on we'll see that even recovering of these kind of the non-evanescent frequency components will become a challenging task if you have the random scattering in the path of the light, in the path of the object and your observation data. So that is the issue. That issue I will try to touch. Okay, so apart from conventional imaging, our interest is also the imaging the complex field, particularly using the holography. There are other methods, the non-holographic methods, but in this talk I will mainly discuss the holography, which gives you different methods to record and reconstruct the complex field. And in fact, you can also apply the holography for the complete wavefront. When I say the complete wavefront, I mean to say complex field as well as the polarization. So I will discuss few of these holographic techniques, not with a coherent light, not with a conventional method, but with the incoherent light, and then how we can recover the phase. Okay, so let me go to the major issue of the imaging through the randomness. And in my talk, I have made the slides in such a way that we will discuss the two different aspects where you have the randomness by compulsion. You don't have any choice. You have the random light and you have to deal with it. And this is one of the examples. Then there are certain examples where you can use the randomness for benefit or for the advantage of the imaging, better imaging. So I will discuss both of these cases. So here, if I consider the imaging, if we have the random scattering in the path of the light turbulence, then what you get, if you have the clear, no turbulence, then you get the Fresnel limited condition. But if you have the randomness or turbulence, you'll get the speckle, and it's averaged more what we call the integrated speckle in the center picture. Okay, this is the one of the one sort of the speckle pattern, but because if the turbulence is fluctuating, so you have a random pattern, and this is one of the random patterns. So you have depending on your interest, you can design and develop different imaging system according to the nature of the speckle, whether the speckle is temporally fluctuating or spatially fluctuating. You have to decide. You have to accordingly design the experimental strategy. Okay, so why do we get this speckle? Very basic explanation that if I consider the coherent light being illuminate, coherent light and illuminating the optically rough target or optically rough surface, you have the random scattering, and those randomly scattered wave fronts are the wavelets. When they propagate and interfere, they make a very complex interference structure, which we refer here as a speckle pattern. And such a speckle pattern, this speckle pattern may have the only intensity variation, but in addition to intensity variation, they may also have the polarization fluctuations. So I will discuss both these two cases. Okay, so why we want to investigate or examine these kind of problems? So here, these are few examples, like looking through the randomness, and then maybe non-line of sight imaging, etc. So this kind of problems, looking through the random light or maybe tackling the problem of the randomly scattered light is a very old problem, and the different methods have been proposed in the past, like adaptive optics, conjugation, and then even some computational methods. But in this talk, I will mainly consider, I will discuss mainly the contribution of the coherence optics, how we can use the correlation features of the random light to build imaging system to tackle the problem of imaging through random scattering. Apart from the speckle by compulsion, we have another areas where you need the what you call the random light or stochastic light, like ghost imaging, even the high resolution imaging where you try to incorporate more evanescent waves by the random scattering. And then there are other computational imaging with the structured light and the single pixel detectors. So you have a broadly, if you categorized, so we can say that depending on your requirement, you can, it's not always the randomness is a problem. In fact, you can use the random light to build several innovative imaging system and very unconventional imaging system. So we'll discuss few of these. Okay. So so if you see the literature, this topic, this subject has, is being explored using different methods, like I mentioned earlier, like adaptive optics, transmission matrix methods, etc. So those methods I'm not covering this talk because of the limited time. I will discuss mainly the very interesting aspect, what we call the speckle memory effect. And the contribution of some groups in this particular area. This speckle memory effect, for example, if you illuminate the light, you see here. So this kind of speckle memory effect is being used to design and develop several what you call the very simple imaging system, not like wavefront correction, using the autocorrelation of the intensity with a phase retrieval. So for example, if I consider the speckle pattern, what we get, the speckle pattern is nothing but the object involved with this randomly distorted the quantitative function. So if I use the autocorrelation of the intensity, we can get this kind of relation, and which gives you the what you call the spectrum. However, from the spectrum, you need some iterative methods like phase iteration algorithm to recover the object. And this topic and this area people have explored for designing different imaging systems. However, in our work, we don't use what we call the phase iteration methods. We mainly rely on using the correlation with holography approach, so that we can tackle the problem of convergence and the phase retrieval, and then we get the more faithful, we can get the faithful recovery of the target. So rather than using the combining autocorrelation with phase retrieval, we follow a different approach, particularly interferometry approach, but interferometry with the coherence weights. Like the coherence function, complex coherence function, follow the wave equation similar, like there is an analogy between the optical field and the coherence function, and we learned a lot from the contribution of Professor Takeda and his group, and during my postdoc, we work in this area, and then we are further extending this topic to taking to different domain. So I will. So let me just connect briefly touch the basic of the coherence and how we can use, and then what we are presently doing at our group at the ITBHU. So when we consider the fundamental features of the light to characterize the light, we use different properties, local and non-local, and particularly the coherence, which is usually measured by the interference. It gives it's very useful in dealing with our making imaging system with a random light. But apart from that, just using the scalar random light, we are dealing with vectorial coherence, where we have to deal with the transversely polarized light. So you need a 2x2 coherence polarization matrix, and all these elements of the coherence polarization matrix are important to analyze the randomly fluctuating polarized light and also in the imaging. So okay, so in the terms of characterization of the light, what we call the Hanbury-Brown-Pierce approach or intensity correlation is a very interesting method. Apart from the lower order interferometer, lower order interferometers are also useful, but in this talk I will mainly concentrate on the intensity interferometer and intensity correlation and then polarization correlation. So I'm skipping the lower order interferometer. So if I consider if I just describe the intensity correlation, so what you get from the intensity correlation, you can get the frequency spectrum, modulus square of the frequency spectrum of the target. So there is one issue, you are getting only modulus square. So depending on what we get and what we are not getting, we can make a plan and design different experimental setups. So I will discuss a few of these techniques. So broadly, if I categorize, I can say that I will discuss the intensity correlation in two different domains. One is the intensity correlation of the scalar light, where polarization is not considered or ignored. And second case, where we are considering the polarization and then building the imaging system. That is the advantage. So first, I will discuss only the scalar case, or the situation where you have the liberty to ignore the polarization. Even if you ignore the polarization, you are not losing much information. You have flexibility. So first I will discuss those cases, and then I will move to the second case where we have to interpret the polarization and then discuss what we'll get. So this is the work which we did long back, 2011, when I was a postdoc at the Takida lab with Dinesh, and then this the work this technique we referred as what we call the photon correlation holography, because if you see the previous slide, I mentioned the intensity correlation gives the modulus square of the coherence function and complex coherence function, and complex coherence function is nothing but the Fourier transform of the incoherent source. So suppose you have the incoherent source, here is the transparency, which is nothing but a hologram in digital, it's a hologram encoded with a certain information, 3D information. And when this hologram is being illuminated with a incoherent light, the speckle patterns which propagates at different places, those speckle patterns will carry information encoded in the hologram. So what we did, learning from the previous, the intensity correlation relation, we recorded different speckle pattern, different depth, and then correlated it. So this was the experimental setup. So this was the hologram which we loaded, and then the hologram was imaged at the ground glass, and then we take the Fourier transform, and then by moving the camera, we recorded several intensity, and then once we correlate the intensity at the focal plane with longitudinally shifted intensity, we get the reconstruction of the different objects which were encoded into the hologram. However, the limitation of this technique is that we did not get the phase because of the phase loss inherent into the intensity correlation. Because you have seen earlier that in Henry-Brown twist approach, if you consider the intensity correlation, 2 spatial point. You can also similarly discuss Henry-Brown in time. Here we are discussing Henry-Brown twist approach in the space, correlating one point, spatial point with another. So what you get only the modulus square of the coherence, and due to this region, we get only the amplitude distribution of the 3D object. In 2017, we developed another technique, what we call the single pixel correlation holography. So rather than eliminating the object with a rotating ground glass, what we did, we introduced a set of the random patterns by the SLM, and only one part was implemented with the experiment, and the second part was just computational. So it's like hybrid approach. So it's like what we call the similar like computational ghost imaging, where you replace the incoherent source with a digital source, and then you do experiment in only one arm, and the remaining second arm you just digitally propagate the random pattern. So how it works? So this is the random pattern eliminating the object, and we record here at the single pixel, and this is fixed. This detector is fixed at particular distance, z equal to 0. Now the pattern which we are loading here at the SLM, we have those patterns in our computer, so we can digitally propagate these patterns without interacting with object, like a ghost imaging, where one arm is interacting with the object, other arm is directly going to the detector. So see exactly like this. So here the speckle pattern, random pattern, which we are loading at the SLM, those patterns are digitally propagated. So we have two situations. One is the optical arm, which we do which is supposed to be optically implemented and detected by a single pixel, and then second arm is digitally propagated. So like the random pattern which you upload on the SLM, you digitally propagate at different z. So if you correlate this distance, suppose -z with single pixel, this one, this one, then you get the object corresponding to a different longitudinal distance or object corresponding to this distance. When you go other side, you get another object. So there is the reconstruction we demonstrated that we can get the reconstruction of the object when we, like here we are getting J, here we are getting, if I correlating at the 0 with 0, I mean Z equal to 0 with computational Z equal to 0, we are getting 0 object here in the center. When we are when correlating optically recorded signal with digitally at 100 millimeter, then we are getting the object here. Okay, so these are few examples which I discussed in the part of the correlation, intensity correlation. But the problem in the intensity correlation is that phase, we lost the phase. So in order to overcome the phase loss issue in the phase recovery problem in the intensity correlation, we proposed a method where this is the target arm which we want to image or which we want to characterize. So we gave an idea that why not you introduce another coherence which you know, like similar like a holography, where you have the unknown object and you are mixing with a known reference. And this is the approach we followed. And once we have the speckle interference, do the correlation and then process it and get the intensity correlation. So this is the speckle pattern in speckle interference. And if you process it, you get the speckle interference, a reconstructed hologram, and then once you have the hologram, you can hologram or whatever information you have, you can reconstruct behind the scattering medium with the help of this known reference. We gave another idea that because the previous idea was based on the off-axis coherence holography. Here we gave another idea where we use the phase shifted, like we gave the phase shifting in the reference coherence function. And once you have the phase shifting, using the well-known phase shifting formula, we can reconstruct the complex. In another approach, we tackle the problem of phase loss in the ghost diffraction. So it's similar like the previous method, but we implemented in the ghost diffraction. So we allowed another known beam with known coherence, and this is the ghost diffraction typical setup. This beam, reference beam, is mixed with this light and then this light, and you detect the two detector and then correlate. One light which is coming from this like ghost imaging is interacting with the target, other light is not interacting. So you record at two detectors, and then once you correlate, you get the diffractions. This is a very recent work where we have again combined the ghost diffraction with the phase recovery, and so I will skip this. So now, in the last part of my slides, a few slides, I will discuss our very recent works on what we call the Stokes correlation. So if this is the information which is encoded in terms of the orbital angular momentum mode. So if I have the object which is considered the composition of the OM mode, and this information is propagating through the random scattering medium. So what we get the speckle pattern, and by correlating the Stokes parameter of the speckle pattern, we get our idea is to recover the composition of the OM mode. So the polarization, in this case, we use the polarization guiding approach. So I will skip this polarization part because it is a very well-known subject. So I will move here directly. So what we do, in this case, we encode our OM mode, the composition of the OM mode in one of the polarization component of the light, and other polarization component of the light is remaining reserved. It's just like a polarization encoding, you are writing information in one of the polarization component, other polarization component is just like working as a pilot. So it's a pilot assisted approach, and then you are sending the entire beam, the entire light encoded with information through the random scattering medium, and then you record the Stokes parameters. And once you have the Stokes parameters, you do the correlation of the Stokes parameters. So Stokes parameter is like a column having 4 elements, column vector. So having 4 elements. And if you do the correlation of the Stokes parameters, you will have the 4x4 matrix. Now, out of the 4x4 matrix, you take a particular combination depending on what is your interest. And so here we have designed the experiment where SLM is encoding the object and other polarization component is intact, and we recorded the speckle 4 Stokes parameters. And then out of the 4 Stokes parameter, we use only 3. And then this is the correlation. So once we have the Stokes correlation, Stokes parameter, we did the correlation spatial because we have only time frozen speckle according to our interest, because the scattering medium is not dynamic. So recording of one speckle or only Stokes parameters of the speckle will be enough. And once we have the averaging of this speckle, we get the reconstruction of the target, here the OM mode. In another work, we have demonstrated the combination of OA modes rather than a single OA mode, because the in more practical case, your object will have many modes, OA mode. So here we have demonstrated composition of the OA modes. So we use the speckle pattern, Stokes parameters, and then these are the combination of the Stokes parameters we OA mode we have. So what we did, we see here the fractional topological charge we use, and the fractional topological charge is composed of, like here, it's composed of -1 and 0. For fractional charge -0.5, for fractional charge 0.5, there is a composition, fractional charge 1.5, there is a composition. So we were able to, with this technique, we are able to recover the OA mode, composition of OA mode. It is the last in this presentation, this is the last, there's a technique which we very recently reported, where our interest is to make a holography, to build a holography reconstruction, coherence holography reconstruction technique with depolarized light. We want to use the depolarization of the light, because usually if the light is depolarized, you have to filter you have to use the, you have to remove the polarization and then filter one polarization and do it. We want to maybe make utilization of the depolarization and then build the complex field recovery. So this is another approach to reconstruct the complex field of the coherence holography. So the idea is that there is the hologram encoding the object, and if this hologram is being illuminated with a random light, random but unpolarized light, we regard the speckle pattern, which is a speckle pattern of randomly unpolarized light, and then we do the correlation, Stokes correlation. So what we did, out of this 4x4 combination, we used only C22 and C32. So we use only these two combinations, and combining these two combinations, we got the complex field. Once we have this complex field, so this is our experimental setup. This was the, okay. So if you see here, this setup, this component is like your combination of WXX and WYY. So what we did, because if the information is encoded in the WXX, so you need WYY uniform. Okay, so you make just like a background. So and the information is only in the XX. So to implement this experimental, implement this idea, we experimentally made this setup. So the hologram is displayed here and then imaged at the ground glass, and there is only expolarization component. Y polarization component is just like making the background, WYY. And we allow this light and maintain this depolarization. So we made the equal weightage of X and Y. So we have the unpolarized light. And once we have the unpolarized light, the combination of Stokes parameters, certain component will become 0. Only certain components will contribute. And using that combination, so we use S2 and S3. And once we have this combination, we can, we reconstructed the complex valued object from the Stokes correlation. So this was the object. I think this is the vortex beam. It's a phase. This is the hologram. This is a number encoded hologram, and it's a phase. This was again vortex beam experimentally, and this is the what we call, this is the number encoded in the hologram, and then it's amplitude and phase. So I think this is the last slide. Okay. So and another work, we have demonstrated that we can build holography. We can use the speckle to build a high resolution polarization holographic microscope. So rather than illuminating object with a uniform beam, we illuminated object with a random light, and then we did the holography. And we noticed that if you do this kind of holography, in what we call the speckle illumination holography, we get the better resolution. So this was a liquid crystal droplet, and you see this was the with uniform illumination, and this is the with illumination with the speckle pattern. So we can use the speckle for to enhance the resolution, and here the resolution is nearly two times improved. And because if you illuminate with a random pattern, is able to incorporate more frequencies which were missing earlier. So with this, I would like to conclude my talk. In this talk, I presented some of our contributions and contributions from ITBHU, and also my old works at UEC, and then what we are presently doing at our group, and some of the possible areas on the coherence optics. Thank you. So with this, I would like to again acknowledge contribution of my students and funding from different agencies from the government of India, and my institute, IIT. Thank you.
Thank you very much. We have some time for quick questions. So please ask your questions or write in the chat. So there is a question that of the various configurations, which do you feel would be most promising for practical applications?
Okay, it depends on what is our requirement. Particularly, I prefer to use the non-interferometric approach, like Stokes, but then still there are certain limitations, like maybe we are able to recover the complex field, but we are forced to use the polarization guiding condition. But that technique is very stable because it doesn't require any interferometric setup. It's a very inline geometry. But the issue is that we need a pilot assisted condition. That is the problem. That problem we have to further maybe examine and remove it.
Well, thank you very much, Dr. Singh, for your wonderful seminar. So we have 10 minutes break, and we shall start the next session after 10 minutes. Thank you.